Hi everyone. So linear programming is going to be a tough topic, especially at first. There's so much information given to us in these problems that we need to organize and sort through, and really just setting this problem up correctly is going to be really important. So we have Stella's farm. Says it consists of 240 acres upon which she wishes to plant pumpkins and squash. The profit per acre for pumpkin is $400 per acre. I'm going to underline that. And the profit per acre for squash is $300. The number of hours of labor available is 3,200 hours. Each acre of pumpkin requires 20 hours of labor, and each acre of squash requires 10 hours of labor. So we want to determine how the land should be divided between pumpkin and squash in order to maximize profit. So we're always going to start by assigning our variables. As I've said in class, you can use X and Y, but I like to use letters that remind me of what they represent. So I'm going to use P to represent the number of acres of pumpkin. I'm going to use S to represent the number of acres of squash. Now the other variable that will eventually come up in our objective function has to do with our goal, which is what we're trying to maximize. In this case, it's profit. But I don't want to use P for profit because I'm already using P for pumpkin. So I want to choose something else. What else could we do? Maybe I didn't really think through this before I started recording. Maybe M for total amount of money. You can choose whatever you want. I'm just going to have M represent profit. All right, our constraints. These are going to be inequalities that have to do with some limitations, some restrictions in the problem. So if we go back and read through, we have a couple of restrictions. First, the number of hours of labor available, 3,200. And another restriction is that her farm, I didn't underline this, but her farm only consists of 240 acres. So let's start with maybe that first fact, that the total number of acres of pumpkin plus the total number of acres of squash must be less than or equal to 240. That is the size of the farm. And then the number of hours of labor. So that's going to use the information that each acre of pumpkin requires 20 hours of labor. So let's do 20 hours of labor times the number of acres of pumpkin. Plus, if you look at squash, that's 10 hours of labor per each acre of squash. And that's got to be less than or equal to 3,200. All right, now the other two constraints that are sort of implied constraints are that the number of acres of pumpkin and squash must both be greater than or equal to 0, saying that they must be positive. So it would not make sense to have a negative number of acres. All right, next we're going to do our objective function, which has to do with what we're wanting to maximize. We want to maximize profit, so we're going to use this information that the profit per acre of pumpkin is $400. The profit per acre for squash is $300. All right, so remember that we're using the variable M to represent profit. I was thinking M for money. $400 times the number of acres of pumpkin plus $300 times the number of acres of squash. Okay, so that is the setup. Our next step, we're going to graph and shade the constraint inequalities as a system of inequalities, which means we're trying to figure out where the shading overlaps. Because we're using different variables other than X and Y, it's important that we first label which axis will represent which variables. So I'm going to have pumpkins on the X-axis, I'm going to do squash on the Y-axis. So let's look at our first inequality. We're going to think about the boundary line equation, which would really be P plus S equals 240. I'm going to do the intercept method. So if you cover up S, if S is 0, the P intercept is 240. If you cover up P, representing when P is 0, the S-intercept is also 240. So I'm just going to pick a location on each axis with a little bit of space above in case my other intercepts are higher. So 240 to 240, we'll go ahead and connect that. And then when we think about the shading, if we do the test point of 0, 0, if we plug in 0 for P and 0 for S, we get 0 is less than or equal to 240, and that's true. So we're going to direct the shading arrows to be toward the test point of 0, 0. Now let's take a look at our other inequality. We can do the intercept method again. So if we cover up P, if that's 0, we're solving 10S equals 3200, divide both sides by 10, and we get the S-intercept to be 320. I'm going to add that a little bit above 240 on the S-axis. All right, now let's cover up S. So assuming that S is 0, we're solving 20P equals 3200, divide both sides by 20, and we get the P-intercept to be 160. So I'm going to show that a little ways below the 240 on the P-axis. All right, so we'll go ahead and connect those. And if we think about that test point of 0, 0, plug in 0 for P, plug in 0 for S, and we get 0 less than or equal to 3200, which is also true. So we're going to direct those shading arrows toward the test point of 0, 0. All right, the other two inequalities we had are that P must be greater than 0, so it's going to be to the right, and S must also be greater than 0. So we're really just looking at the first quadrant, only positive values. And then for the shading, this is the section here where the shading is going to overlap. So let me highlight those boundaries there. So this is kind of the shape that it makes when it's below both of our diagonal lines. So that's going to create 4 vertex points. We have 4 corners. And again, because we're not using X and Y, before we start listing out the vertex points above the vertex column, let's write out the order of which variable goes where. So let's keep it consistent with X and Y. So P is on the X-axis, so let's list that first. S is on the Y-axis. All right, so the first vertex point down here in the lower left, that one's really easy to get. 0, 0, it represents the combination, 0 acres of pumpkin, 0 acres of squash. The next one, we have the point 0, 240. So it could be 0 acres of pumpkin, it could be 240 acres of squash. The next point down here is also an intercept. It represents 160 acres of pumpkin, 0 acres of squash. All right, and to get the last one, so if you remember from our video lesson from Friday, we talked about how to get the point of intersection between these two lines. So those two lines are the equations that are associated with the constraint inequalities. They are the equations for the boundary lines. So we have P plus S equals 240 and 20P plus 10S equals 3200. So we're going to solve the system of equations because the solution to a system is the point of intersection of the two lines. And you can solve that using substitution or elimination. I really like elimination, so I'm going to do that. Of course, there's a couple of ways you can do it. I'm just going to multiply that top equation, everything, by -10 so that I can eliminate the S variables. So that turns into -10P minus 10S equals -2400. And then I'm going to highlight the two equations that I'm adding together so that I don't get confused. All right, so over here we have 10P 10s minus 10s, those are going to cancel. 3,200 minus 2,400 is 800, and then divide both sides by 10. 800 divided by 10 is 80. So that's the p-value of our vertex point. I would plug it back into the first equation, so knowing that they have to be equal to 240, that tells me that the number of squash acres in that combination would be 160. Okay, now our final step, we're going to plug these combinations into our objective function. So here's what I want you to be really careful of. You want to make sure that the first letter, the first variable that you're listing in your points, corresponds with the first variable that's in your objective equation, so that you can think, okay, the first number is going to go in the first spot, the second number goes in the second spot. One of the most common mistakes I see on this is that your variables are switched, and so students will plug the wrong number into the wrong place, which is really a bummer, because if they've done all the other steps correct up until that point, they may still end up with an incorrect answer. All right, so our profit, of course, when we plug in this combination of 0, 0, that's going to be a profit of $0, so that one's probably not going to be the best. Let's take a look at our second combination. So that profit was quite a bit better. All right, so that one was not as good, but let's look at this last combination. All right, so 400 times 80 is going to be 32,000. 300 times 160 is going to be 48,000. So putting those all together, so 32 and 48 is 80. We'll keep those zeros on the end, so look, that's going to be our best combination. So let's go ahead and circle that, and we can say the best combination is going to be 80 acres of pumpkin, 160 acres of squash, and that's going to give us a maximum profit of $80,000. All right, so in this next problem, our variables that we want to think about are the number of train rides that she takes and the number of bus rides. So let's use T to represent the number of train rides, B to represent the number of bus rides. Now this time we're not looking for a maximum, we're looking for a minimum, and the linear programming process can help us find either. So in this case she wants to minimize her cost, so our objective function will have to do something with cost. Let's let C represent that total cost. All right, so let's think about our constraints. So it tells us that every week she must make at least 5 trips. So let's say the number of train rides plus the number of bus rides must be greater than or equal to 5. She plans to spend no more than 6 hours in travel time. So it takes her 1 hour to ride the train, 1.5 hours to ride the bus. So let's do 1 hour per train ride plus 1.5 hours per bus ride. That's got to be less than or equal to 6. Now on this one, we don't really need those other constraints, T greater than 0 and B greater than 0, because since the first constraint says that that total has to be greater than or equal to 5, that sort of takes care of it. So that's implied that yes, it is only going to be a positive number. All right, our objective function is going to have to do with cost. So the train trip costs $6, the bus trip cost $5. So let's use C for cost, $6 per train ride, and $5 per bus ride. All right, so we've got everything set up. Our next step is going to be to graph and shade our constraint inequalities. Let's first start by labeling our axes. So let's do T on the x-axis, let's do B on the y-axis. And so that means that when we set up our points, the vertex points in our table, we're going to want to do them in the order T, comma, B. All right, so our first constraint, we want to think about the boundary line equation, which will be T plus B equals 5. And if we find the intercepts, if B is 0, the T intercept is 5. If T is 0, the B intercept is also 5. So let's go ahead and mark those. We'll draw our first line. Now when we think about the shading, when we plug in the test point of 0, 0, we get 0 is greater than or equal to 5. But that's false. 0 is not greater than 5. So we're not going to shade towards 0, 0. That means that 0, 0 is not a solution. All the points that are on the same side are not solutions. So we have to shade away from 0, 0. So this time we're shading above the line. All right, looking at our next inequality, so we're going to think about the equation 1t plus 1.5b equals 6. If we do our intercept method, if b is 0, so we're covering this whole thing up, the t-intercept is 6. If t is 0, the b-intercept is 4. The b-intercept was 4, the t-intercept was 6. All right, this time when we think about the test point 0, 0, if you plug in 0 for both, we get 0 less than or equal to 6, which is true. 0 is less than 6. So we're going to shade below this line. So notice that although the lines sort of look similar as they did in the last problem, the shaded region is different. So this time we're shading in this little sliver. So now there are only 3 vertex points. And when we're making our list of vertex points, we're always doing the vertex points of the shaded region. All right, so we're going to list them in the order T, comma, B. So the first 2 down here at the bottom, these are easy to get. 5 train rides, no bus rides. Or 6 train rides and no bus rides. This is the one that we have to solve for. So we're going to solve the system of equations that was created by our constraint inequalities, turn them into equations. So t plus b equals 5, and 1t plus 1.5b is equal to 6. So again, substitution or elimination works. I'm going to do elimination again. I'm going to multiply everything in the top equation by -1, because I think it will be easiest to eliminate the t variable by doing that. I'm going to highlight the 2 equations I'm adding together so that we don't get confused. And so the t's are going to cancel. 1.5b minus 1b is going to leave me with 0.5b. 6 minus 5 is 1. Divide both sides by 0.5 and we get 2 bus rides. If it has to equal 5, that means there's going to be 3 train rides. So those are the coordinates of that intersection point, 3, 2. All right, our final step is to plug these combinations into that cost equation. Again, making sure that whatever the first variable is that's listed in your vertex point is the first variable that's listed in your equation, so that you're putting the right numbers in the right spot. So let's see the cost for 5 train rides, 0 bus rides. It's going to be a cost of $30. 6 train rides, 0 bus rides will be a cost $36. And then finally 3 train rides, 2 bus rides is going to be a total cost of $28. So that's going to be our minimum cost. So we want to make sure you're paying attention to if you're looking for a maximum or a minimum. We'll write out our final answer in words because it's asking us how many of each type of ride. So let's say 3 train rides, 2 bus rides for a minimum cost of $28.